All right, so yesterday we actually wrote this question down. I think I went through and highlighted some stuff for you guys, but example 8 says a ball is thrown vertically upward, right? So that's kind of important, the fact that you know it's going up. Okay, tells you that velocity should be positive. They say from the ground. Okay, so that's kind of interesting because if they say it's from the ground, that means that its initial height is going to be 0, right? They say the initial velocity of 60 feet per second. So V sub 0 or V naught, whatever you want to call it, depends on what they taught you. But your initial velocity is 60 feet per second, right? And then they ask us how high will the ball go? Okay. I think yesterday we also wrote, if I'm correct, I put down that we know that our position function is the S variable, right? We call it the S variable. So initial position is that, okay? So the position S at a time 0, that's the 0 inside the parenthesis, right? Because it's S of t. So S at 0 seconds is 0 feet, right? So this would be 0 feet. It's on the ground. And then we talked about initial velocity, and we said, well, the initial velocity, V naught t, what some people will call it, okay? But the initial velocity was 60 feet per second. And I reminded you guys, I think I did, that that was the derivative for position. Did I do that for you guys yesterday? Yeah. Okay. So I want you guys, before we move into this problem, to understand a couple things, okay? When I went through and taught this to you guys a while back about position, okay, so this is position. I told you if you take a derivative of position, we get velocity, right? And if I take two derivatives of position, which basically is one derivative of velocity, we would get acceleration. Okay, we talked about that before. Okay, now the reason why I mentioned that is, and why we're doing this in an integration section is because we're going to work backwards, because they're assuming maybe you don't know the position function. Now, just so you guys know, there is a position function that you're supposed to know that looks like this. If you've taken physics, this will look familiar. Okay, so that's half times the acceleration due to gravity times time squared plus the initial velocity times time plus your initial height. Okay, but you're not supposed to know that. Okay, so how are you supposed to get that equation if you've never seen that equation? So here's the deal. If I integrate acceleration with respect to time, what do you think I get? Yeah, I get velocity. Velocity plus c. Okay? Now, what do you think I get if I integrate velocity? I get position. So this is, plus c again. So this is what we're going to do in this problem. Okay, we're going to take something that we know for a fact, and we're going to kind of work our way backwards. Okay? To find our original function. So I'm going to start with acceleration. And the reason, some people say, well, why don't you start with velocity? Well, velocity is not always 60 feet per second in every real world situation. But it is true that on this earth, acceleration due to gravity is always going to be negative 32 feet per second squared or negative 9.8 meters per second squared. That is a constant. Okay, so I'm going to use a constant value to help me do this problem. Now, again, they want to know how high will this ball go, so I need to find position, okay? But at first, let's start off with acceleration. Now, we do know that acceleration due to gravity is negative 32 feet per second squared. Okay, so I'm going to integrate that. Integrate negative 32 dt. Notice I'm going to integrate a constant that's not 0. So what do? If I'm doing this with respect to t, what's my integral of negative 32 with respect to t? I'll give you a little bit of a hint. It's negative 32 Say again? T, right? X is correct, but t is more correct because it's dt, right? With respect to t. I know the definition said x, but if you look at the definition, it was all with respect to x, right? So negative 32t plus c. So what you guys just found, and I'm going to write this on the left side, is v of t. We just found our velocity function. Okay? So we just found our velocity function. So how am I going to figure out what the value of c is? Well, let's see. We know that v of 0 equals 60, right? I wrote it as s prime of 0, right? It's up here. S prime of 0, which is v naught 0, initial velocity, was 60. So I know that. So I also know that v of t is equal to negative 32t plus c. I just figured that out right now by integrating. So if I plug in 0 for t, I could actually figure out what c is. So let me do that. V of 0 equals negative 32 times 0 plus c. Now you might say, well, how the heck is that going to help me? What's v of 0? 60. So look, I could put 60 equals negative 32 times 0 plus c. So what's c equal to? 60. Now I want to remind you guys of something. This answer here is called a general solution for velocity, okay? That's our general solution for velocity. I just found out what c is. So let me plug it into my v of t equation. V of t is equal to negative 32t plus 60. This equation right here is no longer called a general solution because there's no plus c. This is now called a particular solution. Okay, so I'll write it down right here. This is a particular solution. Okay, this is just a general solution. Remember, the difference between general and particular is that one of them says plus c and the other one actually has a value. Okay, so we actually have figured out a specific velocity equation for this situation. That's why we call it a particular solution. Okay, whereas the other one would be a general solution, but now it depends on what's the initial velocity. Like, what are you going to give me? And I can give you any equation you want. That's the general solution. The particular solution is when we use the information they gave us to find the particular velocity equation, a specific one. Not just with plus c, but an actual value. It might be plus 0, it might be minus 30, it might be plus 80, whatever, but it's particular to our problem. Now, can I find height with the velocity equation? Would that make sense? No, that only gives me speed and direction, right? So I need height. I need position. So guess what I'm going to do with velocity? I'm going to integrate it again, right? So I'm going to find s of t by integrating v of t dt. Okay? So in other words, I'm going to integrate negative 32t plus 60 dt. All right, so I'm going to break this up just because we're still new to this, right? So I'm going to break it up, but I'm probably going to stop doing that by the next section, okay? Because this is just more work for you guys. You kind of have to get used to doing it just piece by piece without having to rewrite it into multiple problems. But for now, we'll break it up. What is, actually, let me follow the rules again just to be a little bit more OCD on it, right? So let's write it out the way they probably want you to do this. So for the first integral, they would probably want me to move the negative 32 out. Now, normally I don't move it out. I just say, don't pay attention to it right now. And then do it after you're done doing your integral, then put it back in. So usually that's what I do. I don't write it out like that, but it's okay if you do. And then the integral of 60 dt, that would be 60 what? T plus c. So notice I already did the integral on the right side. Let's do the integral on the left side. So what is the integral on the left side? Negative 32 times t to the 1 plus 1 over 1 plus 1 plus c. And then plus 60t plus c. Okay, so that's the integral part. Now, 1 plus 1 is obviously 2, right? So we get, if we simplify this and distribute, we should get a negative 16t squared plus 60t plus c. Okay, because t squared over 2 is what you end up with. Now, if you multiply a negative 32 into it, you end up reducing 32 by 2. So you get negative 16t squared plus 60t plus c. Now, if you're wondering, well, wait a minute, the constant was a negative, and then you're adding it to another constant. What do you get? Well, it's still two constants. So two constants still become a constant, right? So just put plus c. Okay? If the constant's meant to be negative, you'll find out as you do the work. Okay? So don't worry. You're not messing anything up. Are we okay so far with the integration? So I have now found out that s of t is equal to negative 16t squared plus 60t plus c. What do I know about position according to the beginning of the problem? What did they tell me? They gave me some information about the position of it. Well, it's thrown upward, but right now you said it? It's 0 at the beginning, right? It's on the ground when this happened. At time equals 0. Okay, so I'm going to say at s of 0, it's 0. So let me plug that in. S of 0 equals negative 16 times 0 squared plus 60 times 0 plus c. Now, s of 0 is 0, right? So I'm going to put a 0 right here. Now, what do I get on the right side? Just c. So what's my value of c? 0. So here's my position function. Negative 16t squared plus 60t. So we just created a position function for this problem. Now, this doesn't mean that I'm done. Okay, by the way, let me highlight the velocity function too. I'm going to go back to it really quick. Oh, actually I did. There it is. So I just found my position function. Now the problem said, how high did it go? How am I going to figure that out? Let's think about this. How would you figure that out? So I'm just going to pause this real quick, give you a minute to think. All right, so like I said, in order to figure out how high something goes, we have to think about velocity and when does velocity equal to 0. So v of t, which I think I wrote in blue, v of t, which was equal to negative 32t plus 60. Is that correct? Yeah. Negative 32t plus 60. I'm going to set it equal to 0. And that's going to give me my maximum. Now, if you're wondering, like, how the heck does he know that's your maximum? Well, remember, to find maximums, don't we take derivatives and set them equal to 0? And isn't velocity a derivative? Right? So you kind of have to recognize that. That way it makes sense to you. Like, oh, this is why I get a high point. This is why I get a low point, because velocity is the first derivative of my function. And according to chapter 3, first derivatives that equal to 0 give me critical numbers, which could be critical points, which could be maximums or minimums, right? So we're going to go ahead and solve for this. So we get 60 equals to 32t. So t must be equal to what? 15 over 8 if we kind of leave it as a fraction. 15 over 8 seconds. Right? So guess what I'm going to do with that time? Plug it into what? Position to figure out how high it is, right? So I'm going to get S of t, which is negative 16t squared plus 60t. And I'm going to plug in 15 eighths. So it's negative 16 times 15 eighths squared plus 60 times 15 eighths. And you get out your handy dandy calculator, right? And it gives you 56.25 feet. Okay, so there's the answer to our problem. This was a lengthy problem, right? But you could do this with physics formulas, of course. Okay, but the point of this lesson is to kind of tell you, like, you don't need to memorize things. That's the nice thing about math, is that most of the stuff that people memorize, math teachers are always saying, like, why are you memorizing that? Like, you could figure it out. You could literally just figure it out. There's no reason why you can't. Like all the trig identities, and if you guys ever happen to take trig again in college, you're going to see every single trig identity that you memorized, all you really need is the Pythagorean ones, and from there you can derive all of them. You don't need to memorize them. You can figure them out. But it takes time and a little bit of training for that, right? So that's why you take classes like that in colleges, because in colleges they show you a lot more theory, why things work, how things work, right? Here we kind of work on the discrete math where you're doing the work, right? So it's just different. Do we have any questions on this right here? So very, very lengthy question problem, right? So, all right, let me stop this here.